Hey guys, Mr. L coming back at you with another video. And in this video, we're going to focus on electrons. We're going to talk about how electrons arrange themselves around the nucleus, calculations to show energy variations between different allowed energy levels, as well as some experiments that show how electrons behave as both waves and particles exhibiting wave-particle duality. So let's get into this video. So let's start talking about electrons. The first thing we're going to need to discuss to understand electrons, though, are waves. So here's a wave, and you probably know a lot of things about a wave. You know the top may be called crest, the bottom between waves is called trough, but the important pieces of wave that we need to know are point to point. So it could be from crest to crest or trough to trough. This is called wavelength. And we use symbol lambda, Greek letter lambda, to symbolize wavelength. The other thing we should notice about these waves is you've got a multiple repeating pattern, wave after wave. The amount of waves per unit time is called frequency, and that's the amount of oscillations per unit time. And we denote this with the letter nu, Greek letter nu. Kind of looks like a squiggly V. So the units on frequency are an inverse second, 1/2, or we could substitute that with unit hertz, Hz. Those are equivalent. So here's an equation that we can use to relate wavelength to frequency. The speed of light, c, which is equal to 3 × 10⁸ meters per second, is equivalent to the wavelength times the frequency. So if we're looking at the difference between two different waves per unit time, one may have a lot of wavelengths per unit time. Therefore, the wavelength is going to be much smaller and the frequency is going to be higher. Therefore, wavelength and frequency are an inverse relationship. So if one of these is going up, the other one needs to go down. So given this equation, we're going to be able to find any value given some data. If we're given the wavelength of a wave, then we're going to be able to take the speed of light divided by that wavelength, and we could calculate the frequency, as well as vice versa. If somebody gave us some data of electromagnetic photon and some frequency of that photon, we could take speed of light divided by that photon's frequency and find its wavelength. So all of these different photons at differing wavelengths and frequencies are part of what is called the electromagnetic spectrum. And that's just the spectrum of all the different wavelengths and frequencies. So looking at the spectrum, we're going to discuss this from the biggest wave to the smallest wave. The biggest wavelength that we have are called radio waves. And radio waves are going to have the lowest frequency. So if you're driving in your car and your favorite radio station is 101.3 megahertz, and you tune your radio to that value, you could calculate the wavelength. We typically use these for communications. The next smallest wavelength down are going to be microwaves. And we've got two major applications of microwaves, one of which is heating foods. You may have a microwave oven in your house, and your microwave oven has a magnetron which scatters these microwaves all throughout the container, causing water particles to vibrate and rotate, dissipating heat into your food object and heating it up. The other main thing we use microwaves for is communications as well. A lot of your cell phones are going to be connecting to towers which are emitting microwaves. The next one, smaller wavelength, are infrared photons, and the way we detect these as humans is by heat. So we can feel infrared photons as heat. Infrared means below red. So the next piece of the spectrum is the visible region, and the largest wavelength on the visible region is red. So infrared falls below red on the visible spectrum. We're most familiar with dealing with the visible spectrum as this is what we detect with our eyes. So our eyes can detect all these different colors, and you may have heard the mnemonic Roy G. Biv, which stands for red, orange, yellow, green, blue, indigo, and violet. Violet has the smallest wavelength of the visible region, highest frequency. The next one on the list is ultraviolet, which means above violet. Ultraviolet is above violet on the visible region, and this is what's emitted from the sun. It's high energy radiation that damages our skin, as well as some organisms can see in this region, particularly things like bees. They can see ultraviolet radiation dissipating off of flower petals. The next smaller wavelength, we've got our X-rays, and if you ever broken your bone, we're going to need some photons that are able to get through our skin and muscle tissue to be able to visualize our bone matter. So our X-rays are even smaller wavelength, higher frequency. Last on the list are gamma rays, which we talked about last video, that are uncharged particles, those high energy photons. So this is the highest frequency photon on the electromagnetic spectrum. One important thing to note here is that all of these photons, regardless of their wavelength and frequency, all travel at the speed of light in a vacuum. It's not that one goes faster than the other. All of these photons go 3 times 10 to the 8 meters per second in a vacuum space. So we just discussed waves. Now we're going to talk about some particle examples. The main guy who studied how electrons move based on these packets of energy is a guy named Max Planck, and he was interested in wondering why objects glowed red, as well as this doesn't really explain things if everything's behaving as waves. So to explain why objects glow red and to help elucidate the ultraviolet catastrophe, he came up with the idea of what's called a quanta. And a quanta is exact value of energy, or a packet of energy that the photon carries that collides with the electron and causes the electron to move from one allowed state to the next. One of Planck's pupils was a very famous scientist, which many of us know, named Albert Einstein. And Albert Einstein helped further this by doing what was called the photoelectric effect. This is what he won the Nobel Prize for. So what he would do is he would take an emitter of photons at certain frequencies and shoot them at metals. And he found that at very low frequencies, nothing happened. But once he would reach a frequency called the threshold frequency, electrons were starting to get ejected. Kind of like if you were playing pool and you were shooting electrons at balls, and then the ball would get hit with enough energy to get ricocheted off of the atom. So this is what Einstein won the Nobel Prize for. He showed that with certain threshold values, particles will collide with these electrons, causing them to eject off of the surface of the metal. Therefore, we could calculate the energy of those electrons being removed by just relating it to the frequency. So using the idea of the quanta of energy Planck came up with, we have this equation. Energy is equal to Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds, multiplied by its frequency. And then you can get the energy of that photon. So if electrons start moving around the atom, this behaves very weird, something that we don't really see with our eyes on a normal day-to-day. But if I were to give you an analogy, if you were to walk up a ramp and you're using your feet, you're walking up a continuous ramp. You could take baby steps, big steps, any step size you want will get you to the top of the ramp. Electrons behave more as a stepwise function, where if you have a staircase and you need to lift your foot up to go to the next stair. So you're going to need to put in energy to resist gravity and lift your foot up to the next step. If you only lift your foot up halfway to the size of the step, you're going to fall back to your original stair because you didn't put in the quanta of energy required to get to the next step. If you put in enough energy to lift your foot above that step, when you fall down, you're going to hit that next step. So this is the idea of what a quanta is and how energies are going to be put in or emitted to cause electrons to go from one allowed state to the next. So a lot of the light that we see is based off of these electron emissions or absorptions. So we have these things called spectra, and there are two different kinds of spectra. You have a continuous spectra, which basically just looks like a rainbow. If you've got white light, it's going to be the entire visible spectrum from red all the way to violet. A lot of elements, though, have only certain areas where electrons can exist in, depending on the shell that the electron exists in. And when you excite these electrons and they fall back down to the ground state, which we'll discuss in a second here, this is going to emit radiation based on that quanta from one state to the next. So something like hydrogen is going to emit 4 different wavelengths within the visible region, and we call this a line spectra. So certain elements are going to have different electron arrangements, and they're going to have different line spectra, which we can use to identify these certain elements. The first famous scientist to start working with hydrogen's emission spectra, those 4 lines from the spectrum, was a guy named Johann Balmer. And he came up with a mathematical relationship to relate these 4 lines to each other. Another scientist named Johannes Rydberg was able to expand this to show that you could relate the wavelength between these different allowed energy states of electrons within an atom, the hydrogen atom. Niels Bohr, which we are going to discuss the Bohr model, which you're probably most familiar with when visualizing the atom, he's going to explain how these line spectrum work. So the Bohr model is based off of the hydrogen atom. You're going to have 1 proton in the nucleus and 1 electron orbiting the outside of the nucleus. The closest orbital that we have is n equal to 1, which we call the ground state. This is the lowest energy state the electron can be in. And any energy, if it's got a certain quanta of energy to allow it to move to the next one, the next orbital is just going to be n equals 2 or n equals 3 all the way out into infinity. So the electron is going to absorb energy to go to a accepted orbital outside of n equals 1, and then it's going to dissipate that same exact quanta of energy to go back to the ground state. So this is an important thing to note, is that only exact accepted values are going to be allowed from the electron to go from n equals 1 to 2 to 3. There are no half values or 2/3 values. Quanta of energy must meet this guideline to go from 1 to 2 to 3. Using the equation Max Planck and Einstein worked with, we could calculate the energy that caused these electrons to go from n equals 1 to any other orbital by just using E equals h nu, the equation we discussed earlier in this video. By using this relationship E equals h nu, this brings us to the equation that's going to have the most interesting or the most useful information that we're going to gather, and that's going to be the change in energy. The change in energy for an electron to go from one state to the next is equal to negative Planck's constant times speed of light times Rydberg constant, which is just a constant. And we're going to multiply that by the 1 over n squared final minus 1 over n squared initial. So if we know the final n value and the initial n value, then we can calculate the energy change associated with that value. With that energy value, we could then calculate the frequency using E equals h nu. And if we know the frequency, then we can calculate the wavelength. So using this equation, we can know the wavelength and frequency of any electron transition within the hydrogen atom. So the Bohr model is a pretty good model to show us how electrons go from the ground state to any other accepted value. But this has some limitations. The first limitation is that this idea only works for the hydrogen atom. Anything with more than 1 electron is going to take so much math, and it's not going to be so useful, and you're going to need a supercomputer to be able to solve this kind of stuff. The other thing that the Bohr model doesn't really address is that the electron's a negatively charged particle and it's orbiting around the nucleus. Then why doesn't the electron just spiral into the nucleus and hit the nucleus and collapse? So Bohr kind of just said that doesn't happen and it's going to be okay. And the third thing is that the electron doesn't really orbit the nucleus like the planet around the sun. That is not how this behaves. And in the next video that's going to come out, we're going to see that electrons behave as cloud probability regions and they vibrate into these different modal shapes. But there are some good things that are taken away from the Bohr model. The first thing is that he showed that it takes a quanta of energy to go from ground state to any other allowed state or in between any other state. So he was using that quanta of energy as well as the idea of the ground state. So the next guy we're going to talk about is a scientist named Louis de Broglie. And he showed the relationship between wavelength of matter and its mass. So he thought that if these photons that are acting as waves can exhibit particle behavior, then bulk matter like you or me, as well as electrons, should have wave properties. So his biggest takeaway from this equation, which is lambda equals Planck's constant divided by mass times velocity, which is momentum. The mass you need to make sure you put into kilogram. Planck's constant is a joule second, and joule is a kilogram meter squared over second squared. So if you want the kilograms to cancel out, make sure your mass has been converted correctly using kilogram as the unit. So his major outcome is showing that the bigger the mass of the object is, the smaller the wave property that it has, or the smaller that its wavelength will be. So we are all basically just waves. I am a wave that you are trying to resolve with your eyes, and the smaller my wavelength is, the less I'm going to look like a wave. But the smaller the mass an object has, the bigger the wavelength is going to be. So you're going to be able to use these properties, such as when we take an electron micrograph. Why we can see the structure of graphene is electrons are so small in terms of their mass, the wavelength is going to be able to resolve those single atom atomic sizes. So the last guy we're going to discuss in this video is a guy named Werner Heisenberg, and he came up with the idea of the Heisenberg uncertainty principle. Here's the relationship mathematically, which is the change in position times the change in momentum, which is just mass times velocity, should be greater than or equal to h over 4 pi. And if you were to rearrange and do some calculations with this to see the uncertainty of the electron within the hydrogen atom, if you were 99% certain of the speed, you would have an area that is 10 times greater than the size of the hydrogen atom of where the position of that electron could be. So the major outcome from this is not to be able to really do the math, is to know that the more you know about the position of the electron within an atom, the less you know about how fast it's going. The more you know about the speed or the momentum of that electron, the less you would know about where it could be. So you have an uncertainty the more certain you are of one thing versus the other. So there it is, you guys. There's the video on waves, the calculations for electron transitions, the Bohr model, as well as the scientists that help to elucidate wave-particle duality. In the next video, we're going to talk about electron configurations and the notations and rules that go along with this. So if you found this video useful, smash the like button, send it to your pen pal overseas, send it to your favorite grasshopper, and we'll see you in the next video.